In this video, we're going to talk about integration on Sage. The command is integral, and it does both definite integrals and indefinite integrals, or antiderivatives. The number of arguments we feed to the integral command determines which one it will be. So first off, let's do the indefinite integral. So we just type the word integral, parentheses, and then we give it the function name, or you can type the formula right here, and then comma, and then the x here is the variable of integration. Now we'll notice in our examples below that Sage does not add the constant of integration. Normally we put a plus c on the end when we have an antiderivative or indefinite integral, and Sage does not do that, so we'll have to remember to add that mentally in our head. So here's a first example. You can type this formula here directly into this integral command. Don't forget parentheses around the top of this fraction and the bottom of this fraction. And this is the answer that comes out. Oftentimes it's hard to read these complicated things, so you can remember to use the show command if you like and make it look a little nicer. So here's the answer that comes out of this. Another comment here, the log in Sage, remember, is the natural logarithm or log base e. Normally, in your graphing calculator, log means log base 10 or common logarithm. Not so in Sage. So just remember that log in Sage means natural logarithm. Now the other thing, when we integrate these by hand, normally inside this log we would put absolute values here around the x squared plus 9. So absolute value there, absolute there. And Sage does not do that. So it's another thing you have to mentally fill in addition to the plus c. Of course, like with all Sage commands, you can also use the function name. If you previously defined the function f, you can use f's name right there in the integral command, and you get the same thing. It is possible to do this by hand. We will talk about this in Calculus 2, that you can break up this fraction into these two things. This is called partial fraction decomposition, and this first one is a substitution problem, which is a Calc 1 problem, I guess. The next one just takes a little algebra to get this 9 out of here, and then you'll end up with arctangent. Alright, here's a second example. So this is a fairly straightforward substitution problem if we're going to do this by hand, and type it here in Sage, and we get this. Remember, plus c we would fill in here. If you take away the x in front, alright, same problem except there's no x here. So without the x, it's not a simple substitution problem. It's actually quite a bit more complicated. The answer, if you compare this here, is just this 3/2 power of a little quadratic. Here we have quite a bit more complicated thing. There's a technique called trig substitution, which you can use to solve this problem. You'll talk about that in Calculus 2 as well. Be careful reading Sage's output here. This little x right by the 4. Notice that the square root symbol stops right at the 4, so the x is actually outside the square root. You can see that clearly up here in this original output. There's the square root. The square root closes right after the 4, times x is outside. Now personally, if I were going to write this by hand, I would put the x in front of the square root so that there's no possible confusion. So just be careful with that. Same thing happens over here. The square root of 3, this is not square root of 3x, it's square root of 3 and then close the square root times x, as you can see right here. It's only the 3 that's in the square root, not the x. So be careful reading this, the output there. To do a definite integral in Sage, it's the same command, integral command. You just add a couple extra arguments. You put the function you want to integrate, the variable of integration, which is usually x for us, and then the a and the b, the upper and lower limit. So lower limit's a, the upper limit's b. It's a comma b here on the end. It's in that order, so lower limit first, upper limit second. Alright, here's an example of that. Here's a definite integral from 0 to 1 of x to the 4th times e to the minus x. Don't forget these parentheses around the power here. Don't forget this explicit multiplication there. And then we just add the 0 and 1 here on the end of our integral. And this is the exact answer that Sage returns here. There's a technique called integration by parts, which you also do in Calc 2. that you could do to solve this one by hand. Then go ahead and convert the answer to the decimal. Remember, if you want to do that, capital N command will do that. Now, Sage can also handle definite integrals that involve other variables. Could an indefinite integrals like this too. So this is purely symbolic integration. The answer is not a number here. The answer is some expression involving the a, b, and c. That's fine. Just tell Sage that a, b, and c are variables and type in the integral just like it is, and you get an answer involving the a, b, and c. And right here, the t is our variable of integration, and we have another variable x in the limit of integration, which is fine. So I told it that t was a variable, integral cosine t to the 5th power, and here comma t, that's my variable of integration. My limits of integration are -1 and x, and this is the answer. Now, some functions do not have elementary antiderivatives. So by elementary, I mean all those functions you learned about in pre-calculus, powers and exponents and logs and trig functions and their inverses. So all those pre-calculus functions were the elementary functions. And for example, e to the minus x squared is an elementary function. You learned about all those functions in pre-calculus. When you integrate this thing, unfortunately, you don't get one of those elementary functions back again. So we don't know a function which is the antiderivative of this thing. When you integrate this thing in Sage, this is a definite integral, so the answer is actually a number here. You get this thing, this is the exact value, 1/2 square root of pi times erf of 1. And I don't know, you've probably never heard of erf before. Erf is abbreviation for what's called the error function. Here's the definition of the error function. The error function is actually defined in terms of the integral of e to the minus t squared. So Sage's answer is kind of circular. Erf1 is basically this integral with some adjustments of the constants. This is where this 1/2 square root of pi comes from. Adjust this constant. So Sage really hasn't done anything but plug in these numbers into the definition of erf. It will convert this to a decimal. Just using the n command, it will convert to a decimal. There's another way to get numerical approximation of definite integrals if it doesn't have a elementary antiderivative. There are other times where Sage is not able to integrate it. This one, it kind of gives you the answer, at least in terms of erf, which you can deal with. There are other examples where there is no named function that's the answer, and so Sage is unable to do the integral except for numerically. There's a separate command for numerical approximations for definite integrals called Numerical Integral command. It has an underscore between there. So here it is, Numerical _ Integral. It's slightly different from the regular integral command. It only takes 3 things. It takes the function or the expression you're trying to integrate, and then the limits of integration. That's it. What's missing is the comma x to specify the variable of integration. And the reason is, since this is a numerical approximation thing, there can be only one variable involved, which must be the variable of integration. If there's more variables involved, then the answer is not a number and you can't do numerical approximation. So you cannot put in the comma x. Even if you try, you'll actually get an error, so you must leave it out. Up here, the regular integral command, if you leave out the comma x, it might give you a warning, but it probably will do it anyway, especially if there's only one variable, and especially if it's x, though it's good to be in the habit of specifying the variable of integration explicitly. But here you must leave it out. Also, this has to be a definite integral. You can't do antiderivative with this numerical approximation, so this has to be a definite integral. Now the output gives us 2 numbers, but these are not 2 answers. The answer is really this guy, 7468, same thing that we got up here when we did the capital N command on this integral. The second number is not another answer. That's actually an estimate of the error involved in your approximation. So numerical integral command is returning a decimal approximation of this integral. It uses some sort of numerical approximation technique. We'll talk about various ones of those in Calculus 2. It's not doing this algebraically, so there's some error involved here. This number is telling you about how big that error is. Now this is not the exact amount of error, but an estimate for the error. What you should notice here about this error is it should always be a very small number. It should involve scientific notation, right there, e to the minus 15. That means the error here is not 8.29, but 0.000000 blah blah blah, 14 zeros, and then 829. So it's this number, this scientific notation. That's a very small number. It's effectively 0. So this is out in the 15th decimal place where the error is involved. So right here, certainly these first several decimal places we can be confident in, which is for most of the time all we really need. Here's an example where the integral command simply can't do anything. Sine of cosine of x, fairly simple function. I mean, these are elementary functions composed together, but when you try to do that integral, it just says integrate this. Integrate is an alternative command for integral. So you could do integrate, integral, those are the same command. So basically the output is the same as the input. It did nothing. Numerical integral, however, can handle this. So numerical integral, sine of cosine of x, and remember, don't put in the comma x, just put in the limits of integration, minus 1 to 1. This is the answer that it gives us. Notice the scientific notation here tells us we can basically ignore the error. This is a good answer. Finally, I want to do a couple applied examples for integrals. We'll talk about a lot more applications of integrals in Calculus 2, but I would like to talk about area under a curve, which is kind of the basic starting point for a definite integral, and also about motion with velocity and acceleration. We talked about those with derivatives. First off, let's do the area one. So example 9, we have the area under tangent of x squared as x ranges from 0 to 1. That is the definite integral from 0 to 1 of this function. And there's another one where numerical integral comes in handy. This is our approximation for that area. Okay, with motion, net change in position is the integral of velocity, the definite integral of velocity. So suppose an object is traveling with velocity 3t to the 4th plus 2t meters per second. How far has the object traveled? Its change in position from t equals 0 to t equals 5 is the integral from 0 to 5 of the velocity function. And so I did integral of this velocity function. Remember here the variable here is t. So make sure, common mistake with students when we deal with t functions, they're so used to putting comma x that they forget to put comma t. Make sure that the variable matches up. And the answer is 1900, so 1900 meters here is the answer. And that's how you can use Sage to do integrals.